Hello, it's a pleasure to present our research on active perception with a vision language model or foundational models and learning from demonstrations at this workshop on challenges in household robotics, part of the International Conference on Social Robotics. My name is Amir Ghalamzan and I am an associate professor at the University of Surrey and director of the Intelligent Manipulation Lab. Manipulation in cluster or clutter is super complex. A sample of cluster manipulation is a strawberry picking when you have strawberries in cluster, and I show you some examples in which we can develop learning from demonstration to tackle some problems in such settings. And another example of manipulation in clutter would be the household robotics, as you see here. So the challenges involved in such complicated, let's say, manipulation problem is that you may deal with soft and delicate objects similar to strawberries or fruits or some other soft delicate objects in household settings. Difficulty in perception, as you see in clutter, you may the robot may look for an object which is partially occluded or fully occluded, so the perception doesn't perform when there is occlusion. There is complex scheduling problem. For example, if you want to tidy up a room like this that you see in this image, there should be a kind of sequence of tasks that should be executed in order to tidy up the room. So the sequence is important because if you just choose to, for example, pick an object or grasp an object which is in a heap or in clutter, it may not be feasible. So you need to first decide which object to pick first and tidy up, and then move on. So other problem includes the hard motion planning and difficult motion control. As I mentioned, strawberries and household robotics, or strawberry picking and household robotics or manipulation are sharing similar challenges, and cluster or clutter is common. That means objects of interest may be occluded. So by fixed camera view, we cannot find object of interest. That means the robot needs to change the camera position in order to see the occluded objects. Moreover, it is not easy to program the robot to interact with all of the varieties of objects in the scene or different configurations of objects in the scene, and learning from the demonstrations will be handy to enable a non-expert to show the robot how to interact or how to perform the task in such situations. So what are the challenges in household robotics? This shows an example of a demo of Aloha mobile manipulation system, which is designed, affordable robotic system designed for advanced robot learning. In this video, you will see how this versatile mobile robot can perform a variety of tasks, such as wiping table, vacuum cleaning, and loading and unloading dishwashers, along with many other impressive capabilities. So you see that the Aloha robot is just performing very dexterous manipulation and dealing with or interacting with different objects, and having such systems in our home would be quite nice to perform all of these tasks when you are out of the home. But what is the intelligence behind all of these cool demonstrations? And all the intelligence behind Aloha system is teleoperation. There is a human sitting close to the remote robot and observe the robot workspace trying to perform different tasks. Look at the teleoperator how moves head in order to look at different from different angles to the object and get a better let's say understanding about the scene. we look at the learning from demonstrations first, and then we continue with one of the active perception approach that we developed. Conventional learning from demonstrations are only working at the trajectory level. It means that we have a data set of trajectories, then we look at different models. We have dynamic movement primitives here. In the core of the dynamic movement primitives, there is a basis functions that you see here. This basis function can span the entire space for the input. And then you have the parameters which defines the goal position. And by that, you can provide the system or this equation with a new goal point where the system can generalize this demonstration to different start and goal points based on the single demonstration. So you see that this is nice. You can provide how to generalize a demonstration of grabbing a coffee mug to different coffee mug location. But that means that for every single individual task, we need to hand design the features, the visual features, which is extracted from the visual information or other sensory information. For example, in our example, coffee mug, we need to hand design the position of the coffee mug and then provide this, extract this feature by computer vision component and provide it to this formulation, where we can have an entire pipeline to grab the coffee mug from different position on the table. But that is limiting. The limiting factor is that for every single individual task, we need to have hand designed features. Even if the learning from demonstration can generalize, but we don't have automated way to generate hand designed features for different tasks. In deep probabilistic movement primitives that maps this visual sensory information to the robot movements. And that means that we process or train the information coming from the visual information and then map it to some discrete weights which are multiplied by the basis function and generate continuous trajectory. And by this, we have a tool that we can change the weights or the different weights of these parameters or these networks that we have here, in order to minimize the distance of the predicted trajectories and demonstrated trajectories. So that is the idea here that we demonstrated. We provide the demonstrations, then the demonstrations goes to this. We extract the weights, and from the weights we train the neural networks or policy extraction networks that can learn the mapping between visual information and these weights, where the new visual information coming from the new scene can generate different trajectories. Okay. So data acquisition, as you see, this is our setting. We had a strawberry picking robot that we tested in commercial field, and we had a problem of generating trajectories per each strawberry, but from different orientations, so that we can deal with the occlusion. If a strawberry is behind the leaf, so we want to go and reach the strawberry to pick, not with a straight line, but going around that leaf. So that means we need to have a distribution of trajectories based on the visual information that we can sample and select the trajectories that go around the leaf. This is the data collection setting. So we had different strawberries here. Then we define the target strawberries, which is based on the scheduling system that can tell us what is the sequence of, let's say, actions for making coffee or picking all these strawberries. So we have first you need to grab this and put it in the coffee mug and then press that one. So this sequence comes from a scheduling system. In our strawberry picking, it comes from a scheduling picking system, and then based on that, we have demonstrated trajectories that you see here, and now we have a data set we want to train our model. This is one sample of demonstration. We use the Franca Amica, as you see, with custom-made end effector for strawberry picking. There is a camera here that you see, and Alessandra is just performing the demonstration to show the robot how to reach target strawberry. And this is the RVS simulation environment. The prediction is doing that one. So as you see, we have an autoencoder extracting features from our image, and then we have the multi-layer perceptron and conditional uh, let's say variational autoencoders, which maps the low dimension feature vectors, or maps the visual information to the weights, and then we generate the distribution of the trajectories. So this is the first stage of our training. We have variational autoencoder and autoencoders that extract the low dimension feature space, feature vectors. This is the reconstructed image of variational autoencoder. And this is unsupervised learning. It means that you can just do it based on the given image to reconstruct the original image. But the low dimension feature vector is compressing the data from the visual information. Now, we take this compressed data, we freeze this encoder part, and we take this compressed information and pass it through some multi-layer perceptron or CNNs that can process that compressed data and map it into the weights corresponding to the demonstrated trajectories for this scene. So that as a whole generate these weights. These weights are multiplied by the basis function, and at the end of the day it generates the trajectories. For a distribution of the trajectories, terminating as a target strawberry, we have the, let's say, different weights. When we compute the mean and variance per each weight, then we get this kind of bars at each weight. And if we sample from these weights, we see that the distribution of trajectory is generated. So the third stage of training is when we say, okay, we now have the encoder trained, the mapping network is trained, but then we want to train the encoder by just considering the loss in trajectory space. So we freeze this multi-layer perceptron, and then what we do, we train further the encoder by giving the loss in trajectory space, and that makes our encoder task specific. It means that it extracts the features from the visual information which are relevant to task, and that increases the performance of our approach, or of our learning from demonstration approach. So at the end of the day, once we sample from this model or the distribution of the weights, what you see is that given a single image, the robot can go and approach the strawberry by different approach trajectories. And that is nice because now we can sample from this distribution and select the approach trajectory that can handle, in some sense, the occlusion. Okay. So, another problem that we see exists in robotic manipulation is the problem of occlusion for perception. So what does it mean? It means that you have the camera position, but from the current camera position you cannot find the object of interest. So what we have done, given the capability of vision language models, we made use of the vision language model, and we proposed that initially this kind of flowchart, or the blocks systems of blocks that enables to get the information of interest in the scene. In this example, you see a mock sitting here. There is a camera in hand, similar to the previous experimentation. We are using UR5 in contrast to the previous experimentation, but the camera in hand is at the wrist of the UR5, and it's looking down at the table, and this is the camera view. So it is the mock plate but the mark is tilted and the inside of the mark is not visible. And the question to the VLM is that what is inside the coffee mug? We built the component which is called perception analyzer, and this perception analyzer analyzes the query together with the image, and it cannot answer the question. So it goes to another block, this blue block, which is enhanced observation. In enhanced observation, what we do, we augment, overlay a 3D grid, a 3D virtual grid, which is like a virtual object in the scene with annotated vertices, and we create that, let's say, grid and project it back into the 2D image. And then what we do, we provide this enhanced observation to the VLM and ask the questions, and we ask how we can move to different vertices or different coordinates of this virtual grid in order to get more information about the question of interest or the query that we made at the initial instance. So what this APP or active perception policy generates is that it takes like all of the history of the visited vertices, observations, the original observation or the initial observation, this observation, and it generates an action for the robot, which is a coordinate for the robot to move and look at the inside of the mug, and also the and the knowledge, which is the cumulative knowledge of the history plus the context knowledge that we provide. So robot goes to new configuration and look at the inside the mug, and from that the robot can see the inside the mug and can then this image is provided together with this image provided to perception analyzer, and now perception analyzer can have a conclusive answer, and the process and loop is terminated. So let's look at this. This is the enhanced observation. Venkatesh is moving the camera and the robot by pulling the robot arm. As you see, the camera is moving, but this virtual box is like a virtual, like this grid is like a virtual box sitting on a table, and the coordinates with respect to the object doesn't change. This is the process. You see that the perception analyzer is asked to perform the task. Then we see activation policy, active perception policy generates the action. Then the robot goes to the coordinate, which is generated here, and then calling perception analyzer. The perception analyzer is analyzing this image, which is what is inside the aluminium fin, and then it gives the conclusive answer, yes. Answer is there is a fork inside the aluminium fin, output stop, and then PA output is true, then the loop is terminated. We had some failure cases. This is one of the failure cases where the robot is going to the correct position but the wrong orientation, so it look opposite to the aluminum fin, which we need to further investigate and make the system robust. One of the things that we need to do and we need to consider is the limitation in the context. So these are the objects that we tested. We tested several different situations. These are the different scenarios that we tested. No active perception, 2D active perception, and 3D with orientation active perception are the scenes and the query that we made. So we tested different, let's say, models with different properties. This is no active perception, 2D active perception, 2D active perception, no annotation, and 3D with discrete grid, and 3D with continuous grid, 3D with continuous, and 3D with discrete and orientation, 3D continuous with one orientation, and 3D continuous with X and one Y orientation, so two orientation. And we see that Here we get the best performance by the 3D with one orientation, and with two orientation we felt that the VLM is getting confused with the settings and it doesn't give us the right answer. So we tested the settings with the toward grounded common sense, where they put fixed cameras and they look at the settings, and we see that toward grounded common sense doesn't give us a good response to select. By selecting different camera views, they cannot answer what is inside the smog, where with more flexibilities our approach definitely can answer the question. And then at the end of the day, we had some scenes in which we have, as you see here, we challenged our approach, and also the approach toward grounded common sense. We intentionally selected scenes that toward grounded common sense doesn't work, and in two settings we see that the APVLM works, but in this one we see that APVLM works 1 out of 5, and we have 4 failures. So there are limitations that we need to look into that and investigate in future works. So in conclusion, household robotics involve many challenges, including perception and manipulation in clutter. Household robotics need advancement in terms of the active perception and interactive perception. We didn't talk about interactive perception. This is our ongoing research. Household robotics need advancement in easy programming as well. So we discussed learning from demonstrations, and what we didn't discuss is reinforcement learning, which is beyond the scope of this talk. By this, I conclude, and I would like to thank people who contributed to this presentation, PhD students and MSc students that work in my lab, Intelligent Manipulation Lab. Thank you very much, and goodbye.